Design Junkie family, you did real work this year. You helped push this podcast into the top 20% on Spotify for 2025. Engineers know progress is never an accident. It takes repetition, curiosity, and a community that shows up. To everyone who rated, subscribed, and stayed in the grind with us, welcome home. You are part of this workshop now, and this milestone is yours as much as mine. And if you are new here, step in and join the crew. Every great build starts with the first cut. Your input matters. Your rating matters. And if you enjoy the podcast, show your support with a like, a follow, or a comment. Let's keep designing, learning, and leveling up together. Welcome to Mechanical Engineering Made Simple. Welcome, everyone. Today, we are strapping in for a massive deep dive that sits right at the heart of the chemical and process industries. We are investigating the entire life cycle of industrial reaction systems.
Right.
We're going from the microscopic physics that govern how two molecules meet, all the way up to the massive multi-ton vessels that contain these processes, and of course, the mechanical integrity that keeps them safe.
Our mission today is explicitly focused on giving you the shortcuts to expertise in industrial process engineering. We've pulled together a huge stack of sources covering everything from fluid mechanics, and we're talking simple Newtonian fluids, all the way to complex slurries, all the way through reaction kinetics, advanced mixing, and the critical engineering standards that govern how you build the vessel itself.
And we are really focusing on that transition, that moment where a process jumps from, optimizing a small batch in the lab to achieving consistent, efficient, and most importantly, safe operations at the production scale. It's a leap that requires a complete shift in engineering focus.
And that shift is all about understanding the link between scales. I think the key knowledge nugget we want you to walk away with today is this. True expertise comes from seeing the relationship between local microscopic phenomena.
Like what exactly?
Things like how fast a tiny eddy dissipates its energy, or how a single solid particle interacts with a fluid boundary layer, and connecting that to the resulting global outcomes.
So things like final product yield or energy usage.
Or even catastrophic vessel failure. If you can connect those dots from the micro to the macro, you've mastered the process.
Okay, let's unpack this. We have to start small because the entire philosophy of a successful scale-up absolutely has to begin in the lab. If you rush the R&D, you're going to pay for it tenfold later on the plant floor.
That is the core principle of process development. You must perform extensive investigative work at the laboratory scale first.
And why is that so non-negotiable?
Because in the lab, you can easily and rapidly investigate a huge number of parameters, temperature, concentration, agitation, speed, different solvents, and you can fail cheaply and quickly. This iterative process at the small scale leads to rapid process optimization before you commit serious capital to steel and concrete.
And the scaling strategy itself needs to be disciplined. The sources are really clear on this.
Yeah.
You should never jump straight from a beaker to a 50,000-gallon reactor.
No, absolutely not. You should utilize several vessel sizes, lab, bench scale, then a pilot plan, and only then move to full production.
The full-scale plant isn't for R&D then?
Its role should not be R&D. Experiments on the production line should be incredibly selective. They're primarily for the final confirmation of your parameters, maybe fine-tuning the last 3% of efficiency, or investigating a problem that's already happening. You need to know the physics works before you hit the big green button.
So to make that stepwise scale-up reliable, engineers lean on standardized equipment. Let's talk about the concept of a standard mixing vessel.
Right, so this is usually defined as a vessel where the liquid fill depth, which we'll call H, is equal to the tank diameter, T. It's a 1-to-1 ratio.
Standardizing that geometry helps minimize the variables when you're scaling up.
It does. But a quick design note for anyone actually specifying these vessels. The overall vessel height should be at least 30% greater than that maximum fill depth.
And what's that extra headroom for?
It's essential for coping with surface splashing, especially at high agitation speeds, and also for accommodating what's called gas holdup. If you're sparging air into a fermentation, for instance, those gas bubbles will expand the liquid volume. You need space for that.
And we're even seeing companies get clever with manufacturing standardization through modular vessels.
Oh, yeah, this is a great efficiency play. They use standardized cylindrical sections and then interchangeable bases, like a torus spherical head, which lets them create a huge variety of vessel configurations using standardized, pre-certified, and easy-to-swap components.
So it's like building with industrial-scale Legos. It saves on custom fabrication costs.
It does, and it greatly speeds up pilot testing when you can quickly assemble and disassemble different tank geometries.
All right, let's move inside the lab and talk tools. For a mixing engineer trying to nail down these parameters, what's in the essential toolkit for measurement?
Well, the basics are absolutely critical. A handheld optical tachometer is essential for checking and calibrating your electronic agitator speed readouts. You can't just trust the dial.
A gut check.
Exactly. You also need accurate averaging voltmeters to read data from things like strain gauges and a precise temperature-controlled recirculation system to ensure thermal stability. Rheology and reaction kinetics are so sensitive to temperature.
But the real complexity, I think, comes in measuring the power input, specifically the torque. This isn't a simple multimeter job. We're talking strain gauges and slip rings.
That's right. Measuring the torque transmitted through that mixing shaft is crucial because it directly translates to the power being dissipated into the fluid. Strain gauges, which measure the tiny mechanical deformation caused by torsion, are typically wired through slip rings or more modern inductive couplings to get the signal off the rotating shaft.
And what's the biggest pitfall in setting that up? Where do people go wrong?
Calibration. It is absolutely non-negotiable, and it's extremely challenging to do right. You have to perform an external calibration using known, quantifiable torques without accidentally applying any bending loads to the shaft.
And bending loads will just confuse the signal.
Completely. It leads to significant errors in your power input calculation.
And placement matters too. Where do these gauges actually go?
If you're just measuring the total power draw, a single gauge set can be placed high on the shaft, above the liquid level. But if you're doing detailed process optimization, especially in a system with multiple impellers—
Say one near the top and one near the bottom.
Exactly. Maybe a feed impeller near the top and a gas-dispersing impeller at the bottom. In that case, you need multiple gauges. They're positioned strategically to measure the torque contributions from each individual impeller, which lets you understand how much power is being consumed in different parts of the tank.
That deeper understanding of localized power is key. Shifting gears slightly, how do engineers quantify the quality of mixing? It feels like a very qualitative thing, but they use blending time or mixing time.
It does feel qualitative, but we have some great quantitative methods. One of the oldest and still one of the most effective is the acid base with indicator method.
Okay, so you're basically injecting a dye that also chemically reacts.
Precisely. You introduce a small pulse of acid or base into the vessel, which already contains an indicator. Something like bromphenol blue, which changes color from blue to yellow, or phenolphthalein, which goes from pink to colorless.
And the visual endpoint, the last little swirl of color to disappear, that tells you something important.
It gives you the point of last mixing. And that location is often the perfect spot to strategically position a conductivity or temperature probe for future process control. You found the worst spot in the tank.
So once that time, which we can call theta, is determined, engineers use the dimensionless mixing time, N theta.
N theta is one of the key scaling parameters in mixing. It's the product of the measured mixing time, theta, and the impeller speed, N. It represents the total number of impeller revolutions required to achieve, say, a 95% state of uniformity.
And if you can keep that dimensionless number constant as you scale up,
you have a very solid basis for transferring the process to a larger vessel with a good chance of success.
And this leads us to a crucial point about homogeneity. Perfect 100% mixing is exponentially difficult to achieve. We actually have formulas to calculate the time required for higher degrees of mixedness.
We do. For example, if you figure out the time it takes to get to 95% homogeneity, you can calculate the time it takes to get to 99% homogeneity just by multiplying that 95% time by 1.54.
The practical implication of that small multiplier 1.54 is massive, isn't it?
It's huge. It tells a designer that achieving that final 4% of homogeneity, going from 95 to 99, requires over 50% more agitation time and energy.
And that difference is critical for costing the power input and maybe avoiding unnecessary energy consumption if 95% is actually good enough for the product spec.
It also reflects the physical reality. As you get closer and closer to 100%, the remaining segregated pockets of fluid become smaller and harder to reach, requiring dramatically more energy dissipation to finally break them up.
Now, a big challenge when taking all these measurements is intrusiveness. Any instrument you put in the tank is going to fundamentally change the flow.
That's the Heisenberg uncertainty principle of chemical engineering. Any probe, whether it's a conductivity probe measuring local solids concentration or an RPD measuring temperature, is intrusive. It's a physical obstacle that can alter local flows and, well, skew the very data you're trying to collect.
So how do you even check if your measurement probe is fouling your own results?
One way is to check for flow separation. For example, if you're using a conductivity probe to measure solid particles in a conducting liquid, you can rotate the probe slowly. If the measured solid's concentration changes as you rotate it, you know flow separation is happening because of the probe's physical presence.
And if you confirm flow separation is happening, what do you do?
The measured value of the solid's concentration will generally be too low because the probe is creating a wake of low concentration fluid behind it. So in this scenario, standard engineering practice is to take the highest measured concentration value you recorded during that test as the most representative value, while acknowledging the inherent limitations of the instrument.
That flows nicely into our next big topic, the dynamics of mixing. The challenge sharpens immediately when the fluid itself is complex, non-Newtonian, or when the speed of mixing competes directly with the speed of a chemical reaction.
And we have to start with non-Newtonian fluids. For engineers used to simple things like water, oil, or ethanol, where viscosity is just a constant number, non-Newtonian fluids are a different beast.
Right.
Here we define the apparent viscosity, μA, not as a constant, but as a function of the shear rate itself.
So the fluid's thickness literally changes depending on how aggressively you stir it.
Precisely. We classify them in different ways, but the sources highlight time-independent fluids. For these, the shear stress at any point depends only on the instantaneous shear rate at that exact point. It doesn't matter how long it's been stirred, just how fast it's being stirred right now.
And in the lab, engineers need proxy fluids to mimic these often nasty industrial conditions.
They do. We use test fluids like carboxymethylcellulose, or CMC, but its solutions tend to be cloudy, which immediately makes them unsuitable for optical visualization techniques like laser Doppler anemometry or particle image velocimetry.
Okay, so what else is there?
Then you have carbopol. It's useful for creating fluids that have what's called a yield stress, but its rheology is extremely sensitive to changes in pH, and for a classic shear thinning fluid.
Where the viscosity goes down as you stir it faster.
Exactly. The go-to is often natrosol or hydroxyethyl cellulose. It produces fluids that exhibit that classic shear thinning behavior, which is really common in things like polymerization and food products.
And the complexity of these fluids leads to a major design challenge, especially in large fermentations or polymer processing, something called cavern formation.
Cavern formation is the classic sign that you have insufficient power input in a highly viscous, shear thinning, or yield stress fluid, like in xanthan gum fermentations.
What does that look like?
The impeller spins, but because the fluid has structural integrity, the mixing energy only creates a well-mixed cavern of high shear, low viscosity material right around the impeller. The vast majority of the vessel's contents just sit there, stagnant and unmixed.
Which is an enormous operational failure. You think you're mixing the whole tank, but you're really just churning a hole in the middle of it.
It creates dead zones where you get huge temperature or nutrient gradients. So engineers have developed models to predict the diameter of this cavern, DC. These models typically operate under the assumption that the stress imparted by the impeller at the cavern boundary is exactly equal to the fluid's yield stress, tall-wise.
It's basically a force balance.
It's a force balance. You're trying to match the mechanical force of your agitation against the internal yield strength of that viscous goo.
And we see extreme versions of this in industrial processes like pulp suspension rheology.
Oh, absolutely. The sources point out that pulp suspensions can exhibit solid-like behavior. They act like a rigid plug, even when they are 90% water by mass. We're talking at only 10% mass concentration.
That is just so counterintuitive.
It is, but the mechanical behavior is completely dominated by the interlocking fiber matrix. To get it to move, you have to overcome the suspension's yield stress, tall Y, which increases dramatically with mass concentration. And crucially, in these pulp systems, the macro flow, the bulk movement, often begins before the fiber flocks are fully disrupted.
So you're moving the whole mass, but you haven't yet achieved the microdispersion you need for an effective chemical reaction like bleaching.
Exactly. It's a huge challenge.
Let's move to the chemical side then. The mixing reaction nexus, specifically micro and meso mixing. This is where we learn that those global metrics, like a 10-minute blend time, can sometimes be completely meaningless.
This is the world of selectivity and yield. In fast chemical reactions, particularly what are called competitive consecutive schemes, where your desired product, R, is prone to reacting immediately with more reactant, B, to form an undesirable byproduct, S, the local mixing time constants control the final yield. not the overall vessel blend time.
Because if the mixing is slow, the reactant you just added, B, finds a huge local concentration of A or R right at the feed pipe, and it leads to immediate overreaction and terrible selectivity for your desired product, R.
And this is a fundamental law. For homogeneous reactions, mixing effects can only reduce the yield below the ideal theoretical maximum. They can never improve it past that point. The moment you introduce a slow mixing step into a fast reaction, you start losing valuable product.
To analyze this problem properly, we have to talk about turbulence scales, starting with the smallest, most fundamental timescale, the Kolmogorov timescale.
Right. The Kolmogorov timescale, tau k, represents the time required for the smallest possible eddy in the flow to dissipate its energy. It's calculated using the kinematic viscosity, nu, and the rate of dissipation of turbulent kinetic energy per unit mass, which is epsilon. This tiny timescale dictates the rate of true molecular mixing, where molecules finally get to touch.
So we have the tiniest scale, micromixing, which is happening below that Kolmogorov scale and is highly sensitive to viscosity. Where does mesomixing fit into this picture?
Mesomixing occurs at the intermediate scales of turbulence. It's controlled primarily by the initial scale of segregation, LS, which is determined by the engineering design of your injection point, like the diameter of your feed pipe.
And that's where most of the reaction happens.
It's where the bulk of the reaction occurs before you get to full molecular contact. And unlike micromixing, mesomixing is less affected by viscosity.
This analysis gives us the critical litmus test for reaction control. The mixing Damkohler number, DAM.
DAM is a magnificent dimensionless number. It's defined as the ratio of the mixing time constant, tau m, to the reaction time constant, tau r. It tells you very simply whether mixing or reaction is the limiting step.
So if mixing is much faster than the reaction, DAM is small, and the reaction is what we call rate limited.
Correct. But where does the mixing start becoming the dominant controlling variable, the part that dictates your yield?
Yeah, where's the tipping point?
Studies show that the critical changes in yield, meaning the process shifts from being reaction-controlled to mixing-controlled, occur when that mixing Damkohler number falls between 0.01 and 0.05. That is the operational danger zone. If your reaction kinetics push you into that narrow band, you must use specialized engineering solutions.
Knowing that 0.05 threshold is an incredible technical shortcut. So what are the practical engineering fixes when you're designing a reactor for a mixing-sensitive reaction in that critical range?
You have to ensure rapid incorporation of the reactant. That means moving away from a single feed pipe and using techniques like multiple injection points distributed around the high-shear impeller zone.
You could also design a rapid recycle loop.
Yes, that draws fluid from the bulk and injects the reactant directly into that high-shear zone right near the impeller tip. You want to get it dispersed as fast as humanly possible.
The sources also point to using inline static mixers for premixing, often right before the main reaction vessel.
They are an excellent solution for this. You'd use a static mixer, maybe with a length to diameter ratio of 4, to ensure intimate, high-intensity mixing over a very short residence time, maybe just 1 second. This guarantees the reactants are fully mixed before they even enter the main reactor, mitigating those large-scale segregation problems.
Now let's pivot to another type of complex system, liquid dispersions, like creating an emulsion. This involves a constant dynamic battle between dispersion breaking drops apart and coalescence, where drops recombine.
And the key concept here is the maximum stable drop size, Dmax. This is the size at which the disruptive forces from turbulence are perfectly balanced by the cohesive forces holding the drop together, that's the interfacial tension, and the drop's internal viscosity.
So if a drop is bigger than Dmax, the turbulent energy rips it apart. If it's smaller, it survives. But the dynamics are complicated by coalescence, the drops sticking back together.
They are. Coalescence depends on 2 independent factors that have to happen in sequence. First is the collision frequency, which is anisity. This is simply how often the drops crash into each other, and it goes up with agitation rate and how much dispersed phase you have.
Okay, so that's the first step. What's the second?
The second is the coalescence efficiency, lambda.
Right.
This is the probability that when they do collide, the thin film of continuous phase fluid separating the 2 drops will drain and rupture, allowing the drops to merge into one.
And here is the truly fascinating and kind of counterintuitive part. The role of local energy dissipation, epsilon.
It creates this conflicting effect that designers have to manage. On one hand, the collision frequency, Begala, increases with local energy dissipation. More power means more turbulence and more crashes. It's simple.
But on the other hand?
On the other hand, the coalescence efficiency, lambda, actually decreases with increased epsilon.
Wait, so crashing them together harder makes them less likely to stick together. Why is that?
Because the duration of the contact is reduced, for two drops to merge, the contact time during the collision has to be longer than the critical film drainage time, the time it takes for that fluid between them to drain away.
Ah, so higher turbulence means they just bounce off each other too quickly.
Exactly. The higher relative velocities lead to shorter contact times, making film rupture less likely before the drops just fly apart again.
And the drainage time itself is sensitive to the chemistry.
Mass transfer between the phases can drastically shorten that critical film drainage time. If you have a solute moving from one drop to the other, it creates local surface tension gradients that destabilize the film, making coalescence much more efficient even at high turbulence.
To handle these highly dynamic, constantly changing systems, liquid dispersions, crystallization, polymerization engineers have to rely on advanced modeling tools called population balance equations, or PBEs.
PBEs are essentially a detailed computational accounting system for the entire particle or drop distribution within a reactor. They track the evolution of the drop size distribution over time.
And what are the four simultaneous events that a PBE tracks?
It tracks convection, so drops moving in and out of the control volume. And it tracks the processes of birth and death. Birth happens either by breakage, where one large drop splits into two smaller ones, or by coalescence, where two small drops combine.
And death is just the reverse of that.
Exactly. Death occurs when drops are lost from a certain size class due to those same breakage or coalescence events. PBEs are incredibly powerful for predicting these distribution changes, especially when you couple them with detailed CFD flow information.
And finally, in these liquid-liquid systems, you can get the dramatic event of phase inversion when the whole system flips, say, from an oil and water emulsion to a water and oil one.
Phase inversion is a very system-specific phenomenon, and it's strongly influenced by the type of surface active agents you have. The critical takeaway from the research is that coalescence, the sticking together of the dispersed drops, typically dominates as the controlling mechanism that triggers the inversion.
So if you want to delay or prevent phase inversion, you need to minimize the factors that promote coalescence.
Exactly. Anything that influences those film drainage rates, like reducing the interface mobility, increasing the viscosity of the continuous phase, or shortening the contact time, these are the critical controls for managing or preventing that catastrophic shift.
Okay, to master these complex dynamic systems, we need eyes inside the reactor, which leads us directly to advanced flow diagnostics. We need to be able to measure turbulence and flow patterns without actually touching the fluid.
And the non-invasive standards here are particle image velocimetry, or PIV, and laser Doppler anemometry, or LDA. They both use lasers and tiny seed particles to gather information, but they provide different kinds of data.
LDA is also called the gold standard for turbulence measurement. Why is it preferred over PIV for that specific task?
It really comes down to scale and speed. LDA uses a very small sensor volume, just a few micrometers in diameter, and has an extremely fast response time. This high spatial resolution lets it resolve turbulence scales as small as 2 to 3 times the Kolmogorov scale, which is essential for getting accurate localized turbulence energy dissipation measurements.
And PIV, on the other hand, gives you the big picture.
PIV gives you a simultaneous snapshot of the velocity field over a large two-dimensional plane. But conventional 2D PIV only measures the projections of the 3D velocity vectors onto that light sheet. If the velocity component that's normal to the light sheet is significant, PIV can give you inaccurate results.
A kind of visual distortion, a parallax error.
Exactly, a parallax error, especially near the edges of the image.
Which means if a designer needs the full three-dimensional flow field, 2D PIV just isn't going to cut it.
You need stereoscopic PIV, or 3D PIV. This setup uses multiple cameras to view the particle movement from different angles, which allows you to measure that crucial third velocity component that's normal to the light sheet and minimize that parallax error. It's much more complex, often requiring high pulse rate lasers to capture time-resolved measurements that show the flow changing second by second.
So moving from measuring existing flow to predicting new flow. Computational fluid dynamics, or CFD, is how we design these complex impellers and vessels before cutting any steel. But modeling turbulence requires huge computational effort.
Turbulence is messy and inherently transient, so we have to use models to approximate its effects. The workhorse models are the Reynolds averaged Navier-Stokes, or RANS models. These are time-averaged, which means they simplify the chaotic nature of the flow.
And for many applications, RANS models are sufficient, right?
They are, particularly for general flow field prediction. Certain RANS variants, like the talk bar model, offer surprisingly good accuracy for specific complex applications, like predicting flow in challenging unbaffled stirred vessels. They offer a good balance of speed and acceptable accuracy.
But if we need to capture the genuine time-dependent fluctuations, the truly transient flow behavior that dictates things like micro and mesomixing RANs fails us.
That's where you have to step up to large eddy simulation, or LES. LES is fundamentally a transient model. It filters out the smallest eddies, modeling their effect with a subgrid scale model, but it explicitly captures the random fluctuations of the medium and large eddies.
So why would a designer choose LES, even with the massive computational cost?
Because it's necessary for capturing unstable phenomena that are critical to performance. For instance, simulating the periodic shedding of hairpin vortices behind the tabs in a static mixer. Those vortices are the key mixing mechanism, and a steady-state RANS model would completely fail to even see them. It's the difference between a working process and an underperforming one.
Speaking of trade-offs, when you're modeling the impeller itself, there are different levels of geometric rigor, trading speed for accuracy.
The simplest, fastest approach is the velocity data approach. This is a steady-state technique where you don't even model the impeller. You just use experimental data to prescribe the time average velocities in the impeller outflow region as a boundary condition, and the CFD solver calculates the flow in the rest of the vessel.
Fast, but not very detailed.
Right. If you want to see the intricate details of the flow interaction between a blade and a baffle, you need a full geometric model. The most common technique here is the multiple reference frame, or MRF model. It's still a steady-state approximation, but it defines the impeller region as rotating relative to the stationary tank, offering a good compromise between fidelity and speed.
And the gold standard, the most rigorous approach.
That would be the sliding mesh model. This is a genuinely time-dependent method. The simulation tracks the actual movement of the impeller blades through the fluid grid, accurately capturing the time-varying interaction between the rotating impeller and stationary elements like baffles or internal coils.
So if you're tracking a transient process, like the time it takes to lift a solid particle off the vessel floor or the flow of gas from a sparger, sliding mesh is basically required.
Exactly. It's computationally expensive, but it gives you the most accurate predictive power for those transient or high-fidelity problems.
Let's apply this diagnostic and modeling knowledge to some specialized industrial mixing problems, starting with fermentation. Bioreactors are primarily challenged by oxygen transfer.
Right. In bioreactors, whether you're growing yeast, bacteria, or mammalian cells, the goal is almost always maximizing the gas-liquid mass transfer coefficient, KLA. This is the rate at which oxygen moves from the gas bubble into the liquid phase where the cells can actually use it.
And we have correlations that link KLA to the physical power inputs.
We do. For standard aqueous media, KLA is correlated to the power dissipated per volume, PG/V, and the superficial gas velocity, VS. The relationship is typically expressed as KLA being proportional to PG/V raised to the power of 0.4 times VS raised to the power of 0.5.
That correlation tells us that both the sheer power input and the gas flow rate are important, but that ratio shifts significantly in high viscosity systems, like those mycelial fermentations we talked about earlier.
Oh, in high-viscosity media, standard radial flow impellers like the classic Russian turbine, they fail spectacularly. They just have poor circulation capacity outside the immediate impeller zone. They create that centralized cavern we discussed.
So what's the engineering solution to overcome the fluid's yield stress and get circulation going throughout the entire tank?
You switch to axial flow hydrofoils, like a Procom or a pitched blade turbine. These are specifically designed to push liquid axially, either up or down, generating bulk circulation loops that can penetrate that high viscosity bulk fluid and get things moving.
And the purpose of increasing that pumping capacity isn't just to make the fluid move, it's to enhance the overall oxygen uptake efficiency.
Absolutely. By improving the bulk circulation, the axial impeller increases the size of that well-mixed, low-viscosity cavern around the impeller. And researchers have shown that the critical factor determining overall oxygen uptake and, crucially, cell survival is the frequency at which cells are circulated through that highly oxygenated, high-shear cavern region and then back out into the bulk.
This concept of cell circulation time distribution, the CTD, is so important that engineers use specific scale-down modeling techniques just to simulate these
They
inhomogeneities.
do. In giant bioreactors, maybe 22 cubic meters in size, you get significant dissolved oxygen gradients. You can model this in the lab using a system of two continuous stirred tank reactors, an STR plus STR system. One STR simulates the highly oxygenated impeller zone, and the other simulates the poorly oxygenated bulk zone.
So you're essentially forcing the cells to alternate between good times and bad times, just as they would circulating in a massive tank.
And this modeling technique has been validated by some really striking industrial results. One study involving large-scale E. coli cultivation using standard Russian turbines showed massive glucose concentration gradients, up to 57 milligrams per liter at the top versus only 27 at the bottom. The cells were starving at the bottom of the tank.
And what was the fix?
They switched the impeller type to SCABA impellers, which provide a combined radial and axial flow pattern. This single change, focusing on improving the circulation time distribution rather than just total power input, largely eliminated those glucose concentration gradients.
Which proves that the flow pattern dictates homogeneity and ultimately the cell's access to critical nutrients far more than just raw horsepower.
It's a powerful lesson, a perfect example of using fluid dynamics to solve a biological problem.
That is a fantastic example. Let's pivot now to industrial pulp bleaching, another system completely dominated by non-Newtonian flocculated behavior.
Pulp processing, where you're trying to separate cellulose from lignin using chemicals like chlorine dioxide, is critically dependent on mass transfer. Even at only 10% mass concentration, that suspension yield stress has to be overcome to ensure the bleaching chemicals can reach the fiber walls.
Here, the kinetics are fast, and the delivery of the chemical is limited by the physical dispersion of those fiber flocks.
And this leads us to a famous case study that perfectly illustrates that newer, higher power technology doesn't always guarantee better results if you ignore the fundamental flow physics. This mill upgraded their old peg mixer to a modern, high-shear dynamic mixer, expecting big efficiency gains.
Luck happened.
The complete opposite. Chemical use actually increased unexpectedly by 2 kilograms of chlorine dioxide per ton of pulp. They checked the machine, the shear was excellent, but the yield was terrible. Thermal imaging eventually revealed the problem.
The cold chemical stream was channeling. It wasn't mixing in.
Exactly. Because the pulp stream was non-Newtonian and behaved like a rigid plug, the chlorine dioxide stream, which was much colder, was just channeling along the side of the pulp plug. The powerful new mixer was just pushing this unmixed plug along the pipe. The mixer never got a chance to do its job because the reagents were poorly introduced upstream.
So the solution wasn't adjusting the new mixer, it was addressing the method of addition.
They solved it by changing the addition method ahead of the mixer, ensuring the chemical was more widely dispersed into the entering pulp stream before it even saw the mixer. This process fix ultimately resulted in a massive saving of 1.5 kilograms of chlorine dioxide per ton over the original installation.
The lesson being, always address your upstream mixing conditions, especially with these high-yield stress fluids.
It's a simple lesson, but an expensive one to learn the hard way.
Okay, we have talked about the science of mixing, kinetics, and flow in exquisite detail. But all of that process engineering is completely irrelevant if the physical container fails.
Yeah.
Now we have to shift our focus entirely to the mechanical and regulatory backbone that ensures operational safety, the design for integrity.
This is the critical transition. We're moving from microscopic turbulence to macroscopic forces and regulatory requirements. And the mechanical integrity of large pressure vessels is governed by incredibly stringent codes, like the ASME Boiler and Pressure Vessel Code, Section 8, Division 1.
What's the general philosophy behind that code structure? Does every single vessel need bespoke, detailed, finite element analysis?
No, not necessarily under Division 1. The code is structured with very high built-in safety factors, and it provides established, proven rules for standard construction details, things like nozzles, flanges, and heads. Because of these conservative safety factors, extensive, detailed stress analysis is often waived.
But there's a catch, I assume.
The catch is the engineer must document that all potential loadings, internal pressure, seismic loads, wind loads, support loads, and thermal loads, have been thoroughly considered in the design. You can't ignore anything.
I think the most fundamental distinction for any pressure vessel engineer is understanding the difference between primary stress and secondary stress. If you miss this, you miss the core of pressure vessel design.
Absolutely. Primary stresses, which we label P, are caused by unrelenting loads. Think of the pressure pushing against the vessel wall or the dead weight of the fluid inside. If a primary stress exceeds the material's yield strength, the resulting deformation is not self-limiting.
Meaning the vessel will just continue to deform until catastrophic failure. It ruptures.
Precisely. They are the ultimate safety measure. Therefore, primary membrane stress, PM, must be kept extremely low, always less than or equal to the allowable stress, SE, set by the code for that material and temperature.
Okay, now contrast that with secondary stresses labeled Q.
Secondary stresses are caused by loads that are self-limiting or relenting. The classic examples are thermal stresses, or what we call discontinuity stresses, that arise at a knuckle radius, or where a nozzle joins the shell. If the material yields under a secondary stress, the resulting small amount of deformation relaxes the stress and the process stops. The stress limits itself.
They're less dangerous, so they're allowed to be higher.
Yes. Because they won't cause immediate catastrophic rupture in a ductile material, the codes allow for a much higher combined stress limit. The combined primary plus secondary stresses, PL plus Q, are often allowed to go up to 3 times the allowable stress, SE, reflecting that yielding in these localized areas is acceptable, provided it doesn't lead to excessive ratcheting or fatigue over time.
Beyond just gross rupture from high primary stress, what are some of the other major failure modes that engineers have to actively guard against in their designs?
A critical one is corrosion fatigue. This happens when 2 different damage mechanisms, corrosion and fatigue from cyclic stress, happen at the same time.
So they combine to make things worse.
It's a synergistic failure. The corrosion process creates tiny pits on the metal surface, which act as perfect stress risers. These pits then become the initiation point for fatigue cracks to propagate under cyclic loading, which can drastically reduce the component's expected fatigue life.
Another major concern is thermal stress.
Thermal stress is classified as a secondary stress because it arises when thermal expansion or contraction is mechanically prevented. This usually happens because of steep linear temperature gradients across the vessel wall, say, when you rapidly quench a process.
And since it's a secondary stress, we know that yielding can relax it, but it still leads to risk.
Right. While it won't cause immediate rupture in most ductile materials, repeated cycling of high thermal stress can lead to failure through low cycle fatigue, or eventually cause unacceptable levels of permanent deformation that might compromise the vessel's alignment or its sealing effectiveness.
Let's look specifically at the mixer's mechanical backbone, starting with the rotating components, like the motor and the drive.
Motor selection typically defaults to a NEMA electrical design type B, which provides normal starting torque and is suitable for most mixer applications. However, if the process requires variable speed, say, for starting up a highly viscous shear thinning batch, that variable speed motor must be specifically rated for operation across the entire intended frequency range.
Especially when operating in explosion-proof environments.
Absolutely. You need to ensure safe and efficient power delivery at all speeds.
Then we need to reduce that high motor speed down to the required impeller speed, which means gear reducers.
Gear reducers are essential, and their efficiency varies widely. High-efficiency helical and spiral bevel gears lose only about 1 to 2% of power per reduction stage. But if you opt for cheaper or higher ratio worm gears, your power losses can jump to 4 to 10%, depending on the ratio, which adds up fast in energy costs over the life of the machine.
And what about the rolling elements that facilitate the rotation itself? The bearings.
Bearings are the contact point between the stationary housing and the rotating shaft. They have to withstand all the radial, thrust, and overturning loads transmitted by the impeller, which are often unpredictable dynamic loads. They consist of inner and outer rings, and rotation occurs entirely on the rolling element's balls or rollers, which reduce friction drastically.
Now to the most critical structural component, the shaft itself. When designing a shaft is the minimum diameter based on pure strength shear and tensile stress limits.
While those strength calculations are mandatory, for a mixer, the critical design criterion is almost always shaft stiffness. You must select a shaft diameter that is large enough to meet the natural frequency criterion.
Why does frequency trump strength here?
Because the shaft has to operate safely away from its critical speed. If the operating speed gets too close to the shaft's natural frequency, vibration amplification occurs, leading to massive dynamic loads that can destroy bearings, seals, and even the vessel itself. Even a shaft that's strong enough to handle static forces will rapidly fatigue and fail if it operates near its natural frequency.
That dynamic load concern is what keeps designers up at night. Let's move to sealing, which keeps the process fluid where it belongs. What are the key industrial choices for process mixing?
For high-pressure, hazardous, or high-value fluids, the industry standard is the mechanical seal, often specified as a double cartridge seal. These are complex devices using specialized face materials like carbon, tungsten carbide, or silicon carbide, and they're pressurized with a clean barrier fluid to ensure zero leakage to the environment.
And why the cartridge design specifically?
Cartridge seals are preferred because the entire assembly, the faces, springs, and barrier connections, comes as a single, preset unit. This allows for easy removal and replacement during maintenance. And critically, it lets you pre-test the seal under pressure on a workbench before it's installed in the reactor, which greatly minimizes installation errors.
And on the complete opposite end of the complexity scale, what's the simplest seal?
The lip seal. It's basically just an elastomer material pressed against the shaft by a small spring. Lip seals cannot hold any appreciable pressure. They're used primarily in atmospheric tanks, or sometimes just to keep dust and dirt out of the bearing housing. They're cheap, but functionally very limited.
Finally, let's talk mounting structures, the beams and structural steel that hold the mixer drive.
This is a frequently underestimated area of mechanical design. The mounting supports must be designed specifically for the dynamic loads created by the mixer, not just its static weight. The forces generated by an unbalanced impeller, flow instabilities, or operating near critical speed are much, much greater than the static weight of the gear drive.
So if an engineer only calculated for the static weight, the resulting support beams would be far too lightweight and would be prone to catastrophic vibration failure.
Precisely. The dynamic nature of mixer loads requires structural stiffening and moment calculations that account for these flow-induced forces. It's a serious concern that is often missed by engineers who are unfamiliar with agitated systems.
Let's tie this mechanical rigor back to the broad requirement for regulatory compliance and manufacturing quality control. For a pressure vessel to operate anywhere in the developed world, it has to pass legislative muster.
The regulatory environment is extremely strict. In the European Union, the design and manufacture are governed by the Pressure Equipment Directive, or PED. Other regions have similar national standards. Compliance is mandatory, and it leads to critical certifications, like the CE mark, which indicates the vessel meets essential safety requirements.
And how does the manufacturing process ensure this quality is actually met? It starts with the most critical fabrication step, welding.
Welding requires mandatory quality checks throughout fabrication. You cannot just trust the welder's skill. Welding procedure specifications, or WPS, and their associated procedure qualification records, or PQRs, are required for all important seams. These documents detail exactly how the weld must be performed for every method used, MMA, MIG, submerged arc, or TIG.
And once the weld is complete, we move to non-destructive testing, or NDT, which verifies the structural integrity without damaging the part.
NDT ensures that any defect size and the total area of defects are within code-acceptable limits. Two key methods are used for checking longitudinal and circumferential seams and nozzles: radiographic testing, or RT, and ultrasonic testing, or UT.
What's the practical difference between those two?
RT, or radiography, uses X-rays to generate a film image. It's excellent at detecting volumetric defects like porosity or slag inclusions. UT, or ultrasonic testing, uses sound waves, and it's generally better for detecting planar defects like cracks. UT is also superior for accurately sizing the depth of a defect. You often use both methods depending on the weld geometry and the type of defect you most expect to find.
After all the fabrication and NDT checks, the final mechanical proof is the pressure test.
Nearly all vessels operating above atmospheric pressure are pressure tested. The goal is to verify the resistance against static stresses and strains under controlled conditions. This test has to be documented. While the factor varies by regulation, some highly specialized vessels might be tested at pressures up to 5 times the maximum working pressure, though most standard pressure vessels use a smaller margin, like 1.3 times the maximum pressure.
And finally, the moment the vessel leaves the shop, handling and transportation. You can spend 1 million engineering hours designing the perfect vessel only to have it damaged before it's even installed.
This is a logistics problem that has to be solved by the design engineer, not the shipping company. Shipping saddles, the supports the vessel rests on during transit, must be designed along with the vessel. They have to be located precisely adjacent to major stiffening elements, like reinforcing rings or the dished heads, to ensure the load is distributed safely.
And during the erection process on site, there are local loads to consider as well.
Absolutely. When you're using lifting trunnions, those temporary lifting lugs welded to the shell, the local loads they impart on the vessel shell must be calculated meticulously. If those local stresses are too high, they can cause buckling or plastic deformation before the vessel is even lifted into place and operational.
We have completed an enormous journey today. We moved from optimizing the local energy dissipation rate in a tiny xanthine fermentation sample all the way to calculating the maximum stress on a high-pressure nozzle under seismic loads. It all feeds back into one fundamental design objective: creating an industrial process that is efficient because it is inherently safe and robustly engineered.
Indeed. We have seen that in many advanced chemical and biological processes, especially these fast reactions or cell cultures, the critical performance metric, whether it's yield or cell viability, is less about the average velocity of the fluid and much more about the instantaneous local turbulent energy dissipation rate, epsilon. This raises a critical and, I think, provocative question for the future of industrial design.
Go on.
In a world of increasing process complexity, how much longer will macroscopic, time-averaged models remain relevant when the critical physics that govern failure and efficiency happen at timescales far, far faster than we can typically measure or model outside of highly specialized, computationally intensive research settings?
That's it for today, Design Junkies. If you're getting something out of this, follow the podcast and leave a review. It helps the whole family grow, learn, and build better together.